Okay, good afternoon to all of you. My voice is clear.
Yeah. Yes.
Okay, good afternoon to all of you. I am Dr. Sandeep Dahake. I am CEO and founder of Precision Private Limited. In the last class, we have discussed related to the custom medical devices and more specifically related to the customized surgical guides. In today's lecture, we will see how finite element analysis playing an important role while development of custom medical devices. So, in today's presentation, I will try to complete three case studies related to the finite element analysis and development of the custom medical models or custom medical implants. In last lecture, we have seen that in the process of development of customized surgical implant or customized surgical guides, four basic steps are important. That are, first one is the scanning to collect the data, to collect the raw data, which may be available in the form of DICOM images. Files may be X-rays, CT scan, CBCT scan, or MRI scan. Once you got this particular data, you have to convert it into some suitable format or suitable data to process further or to design something by taking the help of that raw data. The process is called CAD, that is computer aided design. For this purpose, some special softwares are required like Mimix, Thematic, Geomagic Freeform, Mesh Mixer, and many more. The purpose is to convert your raw data into a useful data for not only the designing of the particular implant or surgical guide, but many times that data has to be useful for some analysis like finite element analysis. So in the step 2, that is the CAD, three important parameters are designing of the customized implant, designing of the customized surgical guide, and the finite element analysis. And in the further processes, we can develop this part by using any rapid prototyping technique and then use this data or this particular implant or surgical guides into the actual surgery. In today's lecture, we will see how this finite element analysis plays important role while development of the customized implants. So in my first case study, that is on finite element analysis on the customized implant in mandible reconstruction after tumor resection, but by using with or without the customized surgical osteotomy guide. Means when you use custom surgical guides and when you not using custom surgical guide, then what will be the effect on the customized implant in the mandibular reconstruction that we will see in this case study. So particularly, this was the case of Government Dental College and Hospital. The lady having mandibular tumor and surgeon performed the case by manual surgical planning. You can see in the figure number C, surgeon has drawn something on the 3D printed model and decide where to perform the cut and what will be the length and size of the implant. Accordingly, he has developed the implant dimensions. He has finalized the dimension and use it into the surgery. Also, what he did, based on this manual surgical planning, he performed the surgery. Now what happened? Here, he has not at all used any custom surgical guide to transfer his manual surgical planning into the actual surgery. He just drawn something on the 3D printed model and manually perform the cutting operation. Based on his manual drawing or manual surgical planning, they have developed the implant and fixed into the surgery. In surgery, what happened? In the figure number D, you can see that because of the manual surgical planning and improper cutting of the bone, because not using the custom surgical guide, there is a huge gap between the implant and the bone. You can see in the figure number D, I have shown by the yellow arrow. You can see all the screws, whatever he has planned and developed the implant, whatever the planning regarding the screw location and screw fixing, that at all not possible because of the huge gap between the implant and the bone. Why this happen? Why this happen? This happen only because of improper cutting of the particular tumor section. So with this, we have check what is the effect of custom surgical guides when used and when not used by using the finite element analysis. So in this particular study, we have taken a one patient. We have taken actually three patients, patient 1, 2 and 3, and divide these three patients into different four different cases. You can see these are the data of three patients, patient 1, 2 and 3, and in one patient we have further categorized it into a four part, that is case 1, case 2, case 3 and case 4. Likewise in patient 2 and patient 3, what we did in case 1, we assume that in case 1 we perform the surgery by using the custom surgical guide. What happened? Because of using the custom surgical guide, there is a zero gap between the implant as well as the bone. You can see in the case 1 of all the three patients, in all the three patients, case 1 we use a custom surgical guide, and because of using the custom surgical guide, there is a zero gap obtained between the implant and bone in both the side, in left side as well as in right side. In further cases, like in case 2, case 3 and case 4, we have not used any custom surgical guide, and because of that, the gap between, there is a gap obtained in between bone and the implant. So in case 2, 3 mm gap obtained in left side. In case 3, 3 mm gap obtained in right side, and in case 4, 3 mm gap obtained in left side as well as the right side. So in all the three patients, similar gap arrangement we have provided, and then further we use this data for finite element analysis to check what is the effect of custom surgical guides when use custom surgical guide and when obtained a zero gap between implant and bone. In the material properties, we use this particular data by using previous literature. We considered mandible cortical bone, where the Young's modulus is around 8700 megapascal and the Poisson ratio is around 0.28. For screws and implant, titanium material has been selected, and for this Young's modulus is around 10,000, 10, 1 lakh 5,000. So, and the Poisson ratio is around 0.3 for the screws and the implant. For performing the finite element analysis, before selecting the mesh size, we have performed the mesh conversion test. This mesh conversion test is important before selecting the mesh size, so that we can check the required time required for the finite element analysis, or any error if happen, that can be sorted out. So we perform a trial by taking the mesh size from 1.9 to the 2.4, that is on the 6 element sizes, and we obtain almost similar result in this particular analysis. We check the on mysis stresses and the deformation with the range of 1.9 to the 2.4. In a particular study, after performing this mesh conversion test, we have finalized the 2 mesh size for the complete study for all the 12 cases. This is the meshing model. We use 3-node tetrahedron element and obtained meshing the node around 56,000 and the elements around 31,000. Then in the ANSYS software, we have given a proper contact between the implant as well as the particular bone. In the screws, we have given a bonded contact with the bone, and with the bone as well as the implant, we have given a frictional contact. For the loading and boundary conditions, we fixed the condyle part of this mandible and applied a load of 600 Newton from the previous literature. This particular implant has been fixed in such a way that in the right side 3 screws are provided and in left side 2 screws are provided, and perform the finite element analysis for all the 12 cases. What we obtained in this particular study, when we use a custom surgical guide, that is our case number 1, in all the patient, there is a zero gap between implant and the bone. In the further cases, that is on case 2, case 3 and case 4, the gap has been varied. In case 2, 3 mm gap on left side, in case 3, 3 mm gap on right side, and in case 4, 3 mm gap on both sides. That is applicable for all the 3 patients. So when you can see the results, that is own mysis stress in implant, then own mysis stresses in the screws and in the screw holes, available screw holes. In case 1, case 2, case 3 and case 4, in the similar manner, we have calculated this results in all the 3 patients. So this is the data of own mysis stresses. Simultaneously, we calculated the own mysis strain for all the 12 cases. Now you can see that when we compare the results, so this is the data of patient 1. What we obtained in patient 1 data. In the patient 1, the maximum, the own mysis stresses in the implant varies around from 500 megapascal to around 800 megapascal. In the screws, in the figure B, you can see in the screws it varies from around 100 to 550, and in the screw holes it varies from around up to the 300 megapascal, and the strain varies from around 0.006 to around 0.008. In the screws it varies from around 0.001 to 0.006, and in the whole screw holes that is from 0 to around 0.04. This data is of the patient's 1 result. Same procedure applied for the patient 2. These are the results of patient 2. And for the patient 3, for all the 4 cases. Now we have taken the mean of all the 3 data, that is case 1 of all the 3 patients, case 2 of all the 3 patients, case 3 of all the 3 patients, and case 4 of all the 3 patients, and calculated the own mysis stresses and strains on the implant screws and the screw holes. You can see that the maximum stress obtained in the case 1 as compared to the case 4 is low. Means the stress obtained is maximum in the case where the gap on the both side is maximum as compared to the zero gap, that is with the case 1. This result obtained not only in the implant but also in the screws and the screw holes available in the bone. The maximum results obtained or maximum higher results obtained where the gap is more as compared to the case 1 where the gap is minimum, that is the zero gap. Same results obtained in the strain side also. The maximum strain obtained in the case 4 as compared to the case 1 in the implant, in the screws as well as in the screw holes. This is the comparative results of um, all the 3 patients. That is patient 1 with the custom surgical guide and patient 3 without using custom surgical guide. The results shown in the implant screws and the screw holes and the strains obtained in the implant screws and the screw hole. We have also performed the statistical analysis with this result. We have directly now compared the case 1 where the zero gap between the implant and the bone compared with the case 4 where the maximum gap available on both the side, that is left side and right side. We found that we perform a pair T test, and with this pair T test we found that we got a significant result when we compare case 1 with the case 4 with the implant screws and the screw holes. All the data is significantly satisfied, statistically significant in the case of own mysis stresses and in the case of own mysis strain. Why this happened? Why we obtained lower stress and strain as compared to the case 4 where the maximum gap available on both the side? Because you can see in the figure the red zone, that is the case 1. You can see in the case 1 the red zone on both the side of the implant. When we use a custom surgical guide, then cutting has been performed properly. Because of the proper cutting, implant has been exactly fitted at the planned location and surfaces of the implants are properly touches to the bone surfaces. In the case 2, case 3 and case 4, because of not using a custom surgical guides and performing a manual cutting, the overcutting has been obtained, overcutting has been happened, and because of that overcutting, that implant not properly fitted at the planned location and huge gap between implant and bone obtained. So you can see in the case 2, case 3 and case 4, the red portion showing the implant which is actually properly fitted with the bone, and this green portion showing the implant not properly fitted to the bone and there is a gap between the bone that is around 3 mm. So this green portion is with the case 2, case 3 and case 4 and not in the case 1 because of the proper cutting. So in the case 1, because of the direct contact between implant and bone, that is zero gaps provides, which increase the fixation surface area over the same length. What happened in the case 1, the fixation surface area is maximum as compared to the other cases. When compared to the area of the other 3 cases, in the case 2 and case 3, where the fixation surface is low as compared to the case 1. Also, due to the increased fixation surface area in the case 1, all the screws has been properly fitted in the case 1, which is not in the other 3 cases. What happened because of that? In the case 4, where the maximum gap between the implant and bone was more, that having more susceptible to loosening of the screws. Why? Because of the higher strength concentrated on the screw holes. How much higher? That is around 37% higher as compared to the case 1, where the gap is 0. Again, if the more the gap, more sensitive to the chipping load variation, and almost develop around 28% increase in the stresses when compared to the case 1, where the gap is 0. So because of that, the fixation of the customized implant should be proper, and this data, this calculation, this result showing the effectiveness of the custom surgical guides in the case of mandibular reconstruction. In case 2, this case is particularly related to the metatarsophalangeal joint, custom metatarsophalangeal joint. In this particular case, a patient was met an accident and broken his 3 fingers of the leg. The finger 2, 3 and 4. These are the radiographs obtained from the patient, the anterior side and the posterior side. You can see first he shown this to some doctor, and doctor fitted this particular pins over there in the finger 2nd, 3rd and 4th. That particular pins are called as the K wire or Krishner wires. But this Krishner wires has not solved the problem. Patient again shown his particular case to different doctor, that is Dr. Ragadate. Now he decided to remove this particular Krishner wires from the finger and use some custom medical implant over there. So in the second figure, you can see he has removed this Krishner wires and he decided to develop some customized implant for this particular broken fingers. So he taken the radiograph, performing 2D sketching, then conversion of 2D sketch into 3D images, conversion into a STL file, then using 3D printing, he developed some custom implants. So in this particular case, he is not using any CT scan. He is using a raw X-ray or old radiographic technique, that is X-ray. And by taking the dimensions from the X-ray, we have developed this particular implant. Then in the manufacturing side, by using the RP model as a pattern, we perform a investment casting by using a SS316L material, perform the sandblasting, burr smoothing and rubber wheel cone polish, and then finally use this particular implant into a surgery. So nowadays we can directly take the dimensions from Mimix and Thematic software and design a custom implant. But in this particular case, we have used a X-rays, and by taking the dimensions from the X-ray, we have developed this implant. So just by taking the measurement of our scale, we have finalized the dimension of particular implant. In this particular radiograph, specially, we have taken the dimensions from head of the particular bone, then neck region, isthmus radius. Isthmus means the narrowest portion of the bone and the length of particular bone. So here two bones are fractured, that is metatarsal and the phalange. So these are the dimensions for the metatarsal bone and the also taken the dimension for the phalangeal bone. Based on this data, we have finalized the dimension for the implants. So based on this particular bones, we have finalized this dimension, like head around 3.9 for second and third bone, then neck dimension, isthmus, and the length for both the metatarsal and phalangeal implant. So if the similar patient required this type of implants, that implant can be directly useful or can directly be inserted into that particular patient's body. But if the patient's dimensions are different, then we have to change this particular parameter, and with this changing parameter we can design another implant, and such type of implants not at all available in the market. So we, based on this dimension, we have using the PROE software design this particular implant, metatarsal implant and phalangeal implant. This is basically a ball and socket type arrangement. So metatarsal having the ball type structure and the phalange having the socket type structure. Then we taken the rapid prototyping model to check the dimensions and other things. And finally, by using this particular RP model as a pattern, we have finally developed metallic implant in SS316L material by using investment casting. We have also performed a finite element analysis in this case. Here we perform linear analysis by using the ANSYS 14. Then with the meshing, we obtain a node around 3000 and 1500 are elements. We imported the data in the IGS format. Also, this implant is uncemented type. Uncemented type is we are not using any cement in the implant. So based on this, suitable constraints are selected. Also, two implants are assembled in such a way that the metatarsal implant having an angle of around 46 degree with the surface. That is because the maximum load is applied on the metatarsophalangeal joint at this angle. Because of that, this arrangement has been provided. Also, around 545 Newton force has been applied to the X direction. That data has been taken from the previous literature. And here again material is SS316L. The Young's model is 5 megapascal and the Poisson ratio is around 0.3. The loading and boundary conditions are obtained from the previous data of the gate cycle. And we have performed the finite element analysis for this particular implant. So you can see in the figure 1, in the loading and boundary condition, we have taken around 46-degree angle with the surface because maximum load is applicable in this particular condition. So we have given around 554 Newton load that is the maximum load, which the data has been taken from the previous literature, and perform a finite element analysis. We obtained that the maximum own Mises stresses are around 176 megapascal. Then maximum displacement in x direction, that is in figure number D, is around 0.024, and maximum equivalent stress is around 0.00088. You can see in the figure number C, and the maximum total displacement is around 0.029. Allowable stress of the material is around 558 megapascal, and obtained stress is around 176. So we assume that this customized implant is within the safety limit. Then after completion of the finite element analysis, we have developed this implant by using investment casting in metal and then actually used in the surgery. These are the results of surgery. Patients have the surgeon in the figure number 3 taken the incision, then perform the drilling operation so that to fit the implant into a metatarsal and in the phalangeal bone, and to obtain a metatarsophalangeal joint. Initially, he completed in the third finger, and then sequentially he has inserted the implant in the second finger. After completion of the surgery, we have also taken the follow-up of the patient with after 1 month, 2 months, 6 months, 11 months, and 24 months. Because of this implant is uncemented type, we have not used any cement while fixing this implant into the patient's body. So you can see up to in the result of 24 months, the implant has been slightly changed his position from the original one. In the first month, implant was as it is. Second also not changed. In 6 months result, it is again not that much change, but some prominent change has been shown in the after 24 months. But otherwise, implant is playing his role properly. What we obtained? The MTPJ implant fabricated considering the patient specific needs. Because of the customization, it is simple, more concise than commercially available prosthesis. This type of specific implants actually not available in the market. Also, instead of as compared to the Krishner wire, these custom implants are giving a proper mechanism to this particular finger. Because of the small size and compact size, the fixation area is less. Surgery is performed through a single and small incision. That is the advantage of this small implant. Also, it is universal implant and can be useful for any patient, but related to that particular dimension. If patient having related patient's bone dimensions are related to this patient, then this implant can directly be used. Otherwise, can change this particular dimension. Also, because of the customization of if the implant, the surgical time can be reduced and easily inserted into the patient's body. In the follow-up result, slight deviation of implant from original position indicating changes in stress and stretch pattern during the locomotion of metatarsophalangeal joint implant. Because as I have already said, this is uncemented type of the implant, and because of the changing the position that and the different stresses and strain, the implant had changed its position. Also, the osteopenia has been seen. That is the deterioration of the bone has been seen because of the using this uncemented type of implant. Again, the another very prominent case study I will complete it in short time. We have performed a dynamic analysis on the hip implant. In the market, there are standard implants are available, standard hip implants are available, but what happened when you use a standard implant and the customized implant? We can see the variation of the parameters of the hip bone, that is the neck shaft angle. You can see in the figure this particular angle, the axis from the head of the femur bone and the axis of the particular femur, the angle between these two axes is called as the neck shaft angle. That is varying from person to person. This is not a constant dimension. Every person having different neck shaft angle. Also, the vertical offset, the offset from the center of the femur head, as well as the this particular position. This is called as the lesser trochanter. You can see in this figure, this particular point is called as the lesser trochanter. The point between this lesser trochanter to the center of particular femur head is called vertical offset, and the the line from this particular center to this vertical axis of the bone is called as the horizontal offset. So these three parameters are important parameter in the hip implant, that is neck shaft angle, vertical offset and horizontal offset. So these three parameters are varying from person to person. You can see the variation in upper three figures. So because of that, and in the market, standard hip implants are available with standard neck shaft angles, standard horizontal offset, then vertical offset. So we want to give a custom surgical guide, custom surgical implant. You can see what happened when using a custom implant and a standard implant by using a finite element analysis. Again, we have taken these two implant. One is the customized implant and compared that one into the standard implant, which is having the neck shaft angle is around 130 degree. In a standard implant, we have slightly changed, that is around 125 degree. In customized implant, vertical offset is around 30.56, and in custom it is 30.60, and horizontal offset is around 37.44, and here is around 35.73. So we have slightly changed the dimension and perform the finite element analysis on this. In this particular case, material SS316L has been taken. The nodes are around 1069 and elements are around 508. As per the different activity like slow walking, fast walking, jogging, stair, upstair, downstair, in all the different activities, different load conditions are applicable in this case. With this loading, we have performed the finite element analysis by giving the constraint to the stem, that is uh, fix this particular stem of the hip implant and apply the load towards downward direction, that is again changing as per the activity. So these are the different loading conditions. These are the different loading conditions that are varying as per the time, with respect to time. So this data is available in previous literature. By taking this data, so you can see we have considered different activities like slow walk, normal walk, then fast walk, upstair, downstair, standing up, sitting down, then standing two legs, then knee bend and jogging. And with respect to time, this loading has been changed in every activity. So here we perform dynamic analysis When we compare the results obtained with this loading and boundary conditions, you can see that with the standard implant, in the case of normal walking, the result obtained is around 175 megapascal, which is around only 89 in the case of customized implant. In the case of slow walking, it is around 178, and in custom, it is around 91. Then fast walking, it is 183, and here in 94. Downstairs, it is 191 and 97. And similarly, with all the activities, you can see around 50% reduction of the stresses, not only the stresses, strains, and the deformation with all the activities. You can see when you check with the jogging, the results obtained, that is maximum stress obtained with the standard implant, is around 331 megapascal, and with the custom implant it is around 169. So the stresses has been drastically reduced when using the custom implant. So these custom implants are preferable as compared to the standard implant and giving a proper result when using the in the body, patient's body. The higher stress concentration is observed in the neck region of the standard implant as compared to the customized implant. When we compared the maximum stress obtained in the neck region in the case of standard implant, but in the case of customized implant, the maximum stress obtained on the point of application of the force, and comparatively that stress is again a lower in the neck section as compared to the standard. The overall displacement is lesser in the custom implant as compared to the standard implant. In totality, this is the novel approach in deciding feasibility of customized implant by the use of finite element simulation. Also, this study justifies the use of customized implant against the standard implant. So this is the benefit of finite element analysis, by which we can easily check our design and directly use this particular implant into the patient's body, because every time you cannot check or check experimentally the stresses, strains applicable on the customized implant, because it requires separate arrangement like separate fixtures to hold this particular customized implant. That is not possible many times. So this finite element analysis plays a vital role while designing the customized implants in various complex surgeries. So this is from my side. Thank you all of you for kind listening.
Thank you so much, Dr. Dahake sir, for such a comprehensive and enlightening session. Your insight into the application of finite element analysis in biomedical engineering have truly broadened our understanding and open up new avenues for research and innovation. We now open the floor for questions and discussion. If any participant have queries or need further clarification, please feel free to ask or put up your queries into the chat box.
So the chiving load, that particular in the first case, we have using around 600 Newton, and that has been taken from one literature. The name of the author is around Dahake. So in this literature, they have using a biting force is around 600 Newton on the left molar. So that data has been directly taken from this particular previous literature.
Sir, there is another question from Dr. Anil Banalkar sir. How validation of FEM results were carried out for CSG and without CSG?
In that case, you have to perform experimental analysis. Only in our case, as I have shown a case of government dental college and hospital, there they perform a surgery without using custom surgical guide. So obtained a huge gap between implant and the bone. So we found that because of the huge gap, that implant may be loose after some time and may require some resurgery. So in this particular case, we wanted to check that what will be the result when using a custom surgical guide. That is, in custom surgical guide, we will get a proper cutting, so the fixation of the implant with the bone with zero gap has been obtained, which is not in the other cases where custom surgical guides not used and huge gap obtained. So if you want to compare or properly validate these particular results, we have to compare the experimental analysis by which we can only check this.
Okay. Next question is from Sudhir Kine. Which type of finite element analysis is better to start the research in biomedical application?
Can you please repeat?
Which type of FEA analysis is better to start the research in biomedical application?
Which type of FEM analysis?
Yes, is better to start the research in biomedical application.
So you can start from the static structural, linear static structural, and then you can go with the dynamic analysis. Even I have already discussed the case, that is the hip implant. There we have used a dynamic analysis, that is load with respect to the time. So as per the condition, you can select this.
There is one more question from Vanalkar sir. Can you give justification why tetrahedral element was selected and why the number of elements selected were 31,081 numbers?
So again, it is based on the mesh sizes. Tetrahedron three node tetrahedron basically useful in all the biomedical application because of the complex geometry. You can use hexagon also for better result, but in most of the cases, because of the complex geometry, this tetrahedron elements are used.
Then he asks, how much is the FEA accuracy?
That again another important question actually. To validate the FEA result, we have to go with the experimental analysis, or again you can go with the comparison of the FEA analysis with the 2 or 3 different softwares. Like nowadays in the mimic software, which means in the latest software, the provision of direct finite element analysis is available in the mimics. So where you can not only the design particular implant, but also give all the material properties, select the element size, and directly create a finite element model which you can further directly use in the ANSYS software. Otherwise, you have to done it by using different software like ANSYS and then compare. So in both the software, you may get a different result. So you can check the range of particular results in between two software. Otherwise, the final results can be validated based on the experimental analysis only. That's the only solution. But what happened? Whenever whenever we are dealing with the custom implants, the you have to not only develop but use into the surgeries. So every time testing of this custom implants by using experimental way is not always possible. So in such cases, we have to trust on this FA result and go with this particular FA results. But in the standard implants, like different companies, branded companies like Indus, Johnson, Stryker, they having a all standard implant. In that particular case, they actually perform a experiment on their particular implant, and based on this data, they have developed their particular implant. But in the custom implant, it is not always possible. So in this particular case, finite element analysis is the only solution. But as we have already compared the results of standard as well as the customized, only because of changing a slight parameter, we are only changing the neck shaft angle. In standard, it was around 130 and we have taken 125 degree. Because of that small change, around 50% stress has been reduced. So that is the need of customization, but every time we cannot go with the experimental. Next question.
Next question is from Sudhir Kine sir. What are the qualities checked consideration into the machine?
So see, we are performing a mesh conversion test. What is mesh conversion test? In mesh conversion test, we have to particularly select first the mesh size. You can select it from a previous literature as well as by user experience. Okay. Now, suppose you have selected a 2 mm mesh size. So with this 2 mm mesh size, first you have to perform some pilot study. With this pilot study, you can check if what results you will get, or is there any or how much time it requires to complete the study, because of the complex nature of this particular object. ANSYS or any FEA tool taken a very or huge timing. And another thing is the descriptive error. So to avoid this particular analysis error and the required time should be less, you have to perform some pilot study. And with this pilot study, also you can take one range, that is I have taken from 0.9, then 2, 2.1, 2.3, 2.4, 2.4. I have taken the 6 different elements and checked the stress results and deformation result. So with this range, I obtained similar result, but with the 2 mm mesh size, the processing time is less as well as no error has been obtained. So you can perform this type of pilot studies and then believe what to finalize.
Sir, there is a question from Muthu Kumar V. Is there any scope for the own startup in biomedical field for mechanical engineer?
So we all are the mechanical engineers, and in biomedical there are huge scope. So you can go with the rapid prototyping technology for the customization of different implants, different surgical guides, not only for the specifically I have told you for mandible surgery, but in previous lecture I have shown you the different surgeries, around 12 different surgeries where this type of custom surgical guides are useful. Whatever the designs I have shown you in previous class, that you need not have to finalize that design only. You are free to design by yourself and as per the requirement of the surgeon. So this flexibility is there. Again, you can select the manufacturing technology. Nowadays, people are developing custom implants by using a metal 3D printer. But when you compare the cost of metal 3D printer with the any conventional machining, the cost is drastically low in the case of conventional machining as compared to the metal 3D printing. So if you want to perform a startup in this particular domain, biomedical, you can go with this technology based startup also. I also want to give one example here. Whenever we go with the customized implant, so basically we are using a metal 3D printing, but the branded company like Stryker, Johnson, they are produce this implant, standard implant in bulk, in masses. So they are not using 3D printers for development of this type of custom implant or standard implants. They are using conventional machining. Why? Because they want to manufacture it in bulk or in masses. So that is the difference. So you can select any gap between the manufacturing wise, technology wise, different elements. Not you can also work on the material side. Nowadays, different materials which are useful in the biomedical domain, like you might have heard or we all have known the material silicon. Silicon is a very famous material, and the use of silicon in biomedical is very high. Different types of silicon prosthesis are available. Different custom implants or custom products like fingers, ears, nose, all required a soft tissues. That soft tissues can be fabricated by using a silicon. So you can select any stream like material wise, technology wise, or different device wise. So this is the vast scope. Everywhere is the scope is vast.
Sir, does mechanical engineer require any skill or resources to?
Exactly.
Okay, okay.
Mechanical engineer, not only the mechanical engineer, but whosoever want to enter into this particular domain or into the startup domain, the resources and skill plays very important role. Initially, when I entered into VNIT Nagpur, only VNIT having the Mimic software and only CAD/CAM center students are using this Mimic. But nowadays, most of the colleges having this type of facilities. Because of that, what happened? The scope of research goes on increasing. So skill is very important if you are entering into the designing and development side. Then you must have to know the modeling software, not only the conventional or software like Proe, CATIA, but now you are when you were in the your graduation, that time you learned that Proe and CATIA, but now you are working in the biomedical domain. So in that particular case, you have to learn some specialized software like Mimics, Thematic. We also having a GeoMagick freeform software, which is equivalent software to the Thematic. Thematic is very good software, but they having very some tools are very good in freeform. So in this particular thing, you must have to know Thematic also and geometric freeform also. Now, if we're talking regarding the finite element analysis, the whatever the implant you are designing, that design based on the anatomical data which we got from the CT scan or X-rays or CBCT scan. So you must know to how to convert this data into a different format where editing can be possible. So many in the case of finite element analysis, when you convert your because initially we are using ANSYS software, And in ANSYS software, the one problem is that you cannot directly import the STL file. If the data is file size is very low, in some cases you may import the STL file in ANSYS and perform the analysis directly. But in many cases, you have to convert this particular STL file into a ANSYS compatible file like IGS file or CATIA file. So in this particular case, you must have to know how to convert that file into a suitable compatible file so that ANSYS can import it and you may perform the analysis. Sometimes you have to reduce the triangles which are available in the STL file by using any tool like Mesh Doctor. This tool is available in Geomagic control software. So these are the different software. All softwares having their own speciality. So as per your requirement, you have to use this and for final work. So skills are very important. Another thing is the resources. So these different softwares also have to be available. Then only you can enter. Otherwise, when you talk about the commercialization, you must have your own license. You cannot download the crack of the software and then sell it into the market. That is not practicable. Also, along with the software, you must have a ISO 13485 certification, because this mimics and thematic software are ISO 13485 certified software. Means if you want to draw a length of 5 mm or 5 centimeter, that should be 5 only, not 4.9 or 5.1. So that capability mimics and thematic having, because of that they having ISO 13485 certification, and that are applicable in, or you can use these softwares in biomedical application because of that. So you cannot means without these certifications and approved software, you cannot use this in startup and commercialize this particular product. So I think I have given an answer.
Yes, yes, sir. Thank you very much, Dahake sir.
Sahu sir has asked some question.
Yes, yes. Sir.
How doctors are aware with this availability of all this technology? Sir, actually, what happened? We are in a startup field, so or whatever we are designing, it is only for the doctors. Being an engineer, we can design and develop, but all the problems are the doctor's problem. They every day facing in a surgery or different practices. So problems are directly came from the doctor. By taking this problem, we use our resources to solve that particular problem. So doctors means first you have to approach the doctors. If you having any problem, he can tell the problem, and based on this you have to give the solutions. Also doctor every day he also gone through different literature, so he having the knowledge regarding this finite element analysis as well as the different manufacturing technology. But the only thing, they do not having any resources and they don't know how to use these particular resources. So with the collaboration with the doctors and by using the knowledge of medical and engineering, it is only possible to design. Otherwise only doctor can't do anything, and only engineers also lonely can do anything. It is a collaborative work. Another question is high stress concentration leads to crack initiation, how to overcome? So in that case, sir, you have to change your design. That's why we are doing finite element analysis to check what is the level of the check. Is there any changes required in the design? It is in safe limit or not? So to obtain this particular answers, we have to perform this finite element analysis and check whether the design is safe or not. So, any other question? If FEA analysis results is not fair, what would do? Okay. If FEA analysis is results are not fair, then in that case you have to compare your results with different FEA modules, even though that results are not comparable or fair. Then in that case you have to first compare your results with the previous literature. Again, if it is not related to that, then in that case you have to perform an experimental analysis. So with these 2-3 methods, you can compare your results and finalize the results whatever you got.
Okay, I think questions are over. Very nice presentation, Dr. Sandeep. Hello.
Hello, sir.
I want to add one thing that actually I received so many phone calls also regarding our FDP, okay, from my colleagues for कि really बहुत अच्छा FDP था करके. So obviously it is only due to you peoples which you have delivered very nice informative sessions, and they were really impressed, and especially they called me. I think many phone calls I received in 2-3 days. कि बोले सर इतना अच्छा ये यानी बहुत ही बढ़िया था, यानी ऑल सब इंफॉर्मेशन एकदम परफेक्ट थी, यानी प्रैक्टिकल बेस्ड है. तो मैं बोला थैंक यू. हमारे स्पीकर भी वैसे ही है, एट पार आहे. डहाके सर असो किंवा आपले आशुतोष बागडे सर, इवन पीयूष, सो इट्स ऑल द अभी पीके जैन सर का भी है सेशन.
They all working in the biomedical domain from last 10 to
Yes,
15
yes,
years.
yes.
So
We have
because of
selected
that,
such peoples only, not
they having a
kind of.
huge knowledge.
Abhi now,
Even Dr. Ashutosh Bagre is actually in a medical college. So he having a more practical knowledge in the case of animal studies and actual surgeries. So this is more beneficial for the participant.
Abhi Dr. Prashant Kumar Jain sir, he is a professor at IIITM Jabalpur.
Yes, I
Okay.
know, sir.
I
Everyone
was
knows.
there. Yes, yes, yes. I was there. I have done my PhD from there, na. So
Yes.
he was like my co-guide. So he is also going to deliver a nice session. उनका भी खतरनाक बहुत जबरदस्त स्टडी है. So many research like Dr. नरेंद्र कुमार जो है या मोहम्मद तौफीक है, they उनके वो ये है गाइड है. Okay, over to Nilesh Nirwan, Doctor.
Yes, sir. Thank you, Dahake sir, for such a comprehensive and enlightening session. On the behalf of everyone present here, I extend our heartfelt gratitude to Dr. Sandeep Dahake sir for sharing his valuable time and knowledge with us. This session has truly been remarkable for the learning experience. Thank you very much, sir.
Thank you all of you. Thank you all the participants for kind listening. If you having any question, any doubts, you can always collaborate me, always contact to me. Thank you all of you.